Hello everyone, I'm Cho John, and this video is to go through the sample code of lab week 4A lab line by line. So week 4A lab is for the optimal projects. It is mainly a time series analysis. So for this project, we need a special package called RUGarch, which is enables us to perform time series analysis based on the ARMA-Gauge models, which is a relatively advanced time series models. So for the optimal project, we will have 127 stocks, but in this lab, we only have we only need to analyze the data for one stock. So let me first load the data. You can see that please make sure that your data is in the same path of your RMD file, so such that you can easily load the data from the same folder. So you can see that the dimension of this stock is 150K. No, sorry, it's 1.5 million, right? So it is a huge data set. Although we just look at the stock data for only one stock, it is a huge data. This is because we have many different 10-minute time intervals. You can see that it is indicated by the column time ID. So for stock one, it has around 3,000 time IDs. So each time ID corresponds to a particular 10-minute time interval. So all these 10-minute time intervals are not necessarily in a sequential manner, but they are consistent across the different stocks. So if stock one have a time ID 5, and if you see, say, for stock two, you also have a time ID 5, then this means that the corresponding information like bid price, ask price are in the same time for stock one and stock two. So again, time ID are not necessarily sequential, but time ID are identical across different stocks. So this could enable you to jointly analyze different stocks within the same time ID, so that you can improve the accuracy of the prediction. So after we load this data, we will build a model for each time ID and for each stock, and later on we will see it explicitly. So after we have loaded the data, we need to compute some key statistics like the bid-ask spread and the weighted average price. And these statistics are very important for us to do prediction. And based on the weighted average price, we can compute the log returns. And based on the log returns, we can compute the realized volatility. So this is a logic chain based on from WAP to log return, then to the volatility, realized volatility. This is what we want to predict in this project. So remember the WAP, the weighted average price, the formula is given in the lecture notes. That is the bid price 1 times ask size 1 plus ask price 1 times bid size 1 divided by bid size 1 plus ask size 1. This is explicitly given in the lecture notes. You just copy paste this formula here to compute the WAP. And the same thing to compute the bid ask spread. You can also find the formula in the lecture notes. It's ask price 1 divided by bid price 1 minus 1. And we use this mutate function to add 2 columns to the data frame. Remember, the original data frame have time ID indicate which 10-minute interval this stocks is in. And the second column is seconding bucket. So it's 0, 1, 2, 3. We look at the price of this stock at a 1 second resolution. So this column means this is a 0 second in this 10-minute interval, 1 second in this 10-minute interval. So it is a 10-minute interval. So in seconds, it never exceeds 600. This is second price. And we can see the highest bid price, lowest ask price, and second highest bid price, second lowest ask price, and the corresponding size of the data. And here the stock ID. So if we look at the stock one, for this column, all the values will be 1. So I just added 2 new columns, WAP, weighted average price, and bid ask spread to this data frame. So now, originally, I think this data frame, what is the dimension? 11 columns. Now, after this operation, I added 2 columns. I think now there are 13 columns. We added 2 columns, the weighted average price and the bid ask spread. Remember, the weighted average price and the bid ask spread are computed based on the price and size at a specific time point. So for each time point, I can compute a corresponding WAP and bid ask spread. So that's why we can add 2 columns here. And based on the weighted average price, we can also compute the log returns. And to look at the log returns, we need, say, we want to compute the log returns at time t. Then we not only need the WAP at time t, but also the WAP at time t minus 1, so that we compare the 2 prices to compute the log returns. So the original problem asks us to compute the log return of stock 1 when time ID equals to 5. Yes, this is the, you can see this is the time ID 5 and the seconds in bucket 16. So to compute this log returns at this specific time point, we need the WAP at time 16 and the WAP at the previous time epoch, which is 15, so that the log return is just, we take the ratio and then take the logarithm. This is the log return. So you will see the log return is minus 0.003, something like this. Okay, and then we can use the 2 added columns, the weighted average price and bid ask spread, to compute the realized volatility. So before we compute the realized volatility, this question asks us, so we consider the first 500 time IDs of stock 1 for illustration. To describe what do the following lines code do. So this chart may take up to 1 minute to run. Okay, so remember I said for stock 1, we have around 3,000 time IDs. So meaning that it has around 3,000 different 10-minute time intervals. So we look at only 500 of them. So we just extract the first 500 time IDs for stock 1. So actually this is to create a list so that we will store all the results in this list. And this line is to just extract the first 5 time IDs of stock 1. Remember, the first column of stock 1 is just the time IDs. I just using a slicing operation to extract the first 500 time ID. Then I use a for loop. For each time ID, I just find this is the second of stock 1 for these time IDs. Remember here I pour the seconds in bucket. Essentially this is the second row here. So you may wonder why I need to do this. If you just look at this column, it seems that the seconds in bucket is in a continuous manner, 0, 1, 2, 3, 4, 5, 6, all the way to 600. But this is not true, because at some specific time point, we do not have any trading record, meaning that the weighted average price at this specific time point just keeps a constant. So the log returns at this time point at which no trade happens is 0. Okay, so we need to extract this second information so that, say, if the data is 0, 1, 3, 4, 5, then we're missing a 2 here. And later on, we will just insert 2 between 0, 1, 3, 5 and tell the corresponding log returns is 0, because there's no trading at the second 2. Okay, this is why we need to extract this information here. And correspondingly, I will have the weighted average price for a specific time ID for a specific stock ID. So this is just the price. Then to compute the log returns, we need to compare the weighted average price at the current point with the with the WAP at the previous time points. So I just here -1, I just look at remove the first observation. So now the I can see the price from the second point to the last point. And here is the price from the first point to the second last point. So if I divided them and take the logarithm, it's just the log returns at time 2, 3, 5, 6, all the way to the final time point. Okay, then I just say I create a data frame. This is the corresponding seconds, and this is the corresponding log returns. I just create a data frame and put this data frame in this list to store the corresponding data. And then the following lines is just insert 0 to this data frame. Remember that if I observe 0, 1, 3, 4, 5 in the second column, in the seconds, 0, 1, 3, 4, 5, meaning that 2 is missing. 2 is missing, meaning that in the second 2, there's no trading. So now I need to insert 2 in this data frame, and corresponding to time 2, the second 2, the corresponding log returns is 0 because there's no trading. So I need to insert these informations to the data frame. And so this is just, these lines is just insert 0 into the data frame. So it first says that, oh, I will see which one from the first second to the 600 second, which one is not in the time. So if it is not in the time, it meaning that the corresponding time, say for the second, for the second 2, there's no trading. So I just add the corresponding second, the corresponding time, and the corresponding log returns to this data frame. Why is 0? Because there's no trading. No trading means log returns is 0. I just added this information to the original data frame. And then for ease of analysis, I just order again according to the time, such that the time column just starts from 0 and 0, 1, 2, 3, 4, 5, all the way to, I think, 599, the last second in this 10-minute time bucket. Okay, so you can see this is essentially what these lines do. It's just extract the time information and the log returns information of a specific stock with a specific ID. And for each time ID, I just store the corresponding data frame as one element in this list, log R1. Okay, and later on we will use this list for analysis. With the log returns, I think now I can compute the realized volatility. Remember, the realized volatility is defined in a specific time interval. So in this lab, we'll look at the realized volatility within each non-overlapping 30-second time interval. Remember, for each stock, we have multiple 10-minute time buckets. So for each 10-minute bucket, I divide it into non-overlapping 30 seconds time intervals. So this means that we have 600 seconds, we divide it by 30 seconds. Now we'll have 20 non-overlapping 30-second time intervals for this 10-minute time bucket. Okay, then for each 30-second time interval, I will compute the corresponding realized volatility. Then the total number of realized volatility for one 10-minute time bucket is 20, 600 divided by 30. Okay, so what is the formula of the realized volatility? You can also find this formula in the lecture notes. So essentially, it is just the sum of squares of the log returns within this 30-second time interval, and then we take a square root, right? So this is just the function to compute the realized volatility. Sum all the square of the log returns and then take the square root. This is just function. And now then I apply this function to different time IDs. Remember, we look at the first 500 time IDs for stock one. So I just say this is the corresponding time bucket. Remember, we have 600 seconds in one 10-minute time bucket. So if I just divide it by 30, this thing is kind of a index. So I add a column to say which one is the current time falls into the 30-second interval. So say if it is the first 30-second interval, then the corresponding index is 1. If it's in the second 30-second interval, the corresponding index is just 2. So this column will start from 1 to 20. So indicating that which one corresponds to the original seconds, just meaning this one. So with this index, I can use an aggregate function in R to compute. Wow, this is the realized volatility in the first 30-second interval, second 30-second interval, third 30-second interval, something like this. And then I just change the column name. So the first column is time bucket, and the second column is volatility. So you may need to run this for loop by yourself, or just run these 3 lines by yourself to see how this code works. Because if you just directly look at the data, you may wonder why we have an aggregate function here. So the best way to understand these 3 lines is just say you can set I equals to 1, and then you just run these 3 codes, and you will see, oh, this is essentially computed the realized volatility for each time bucket. Okay, so let me run the code. It takes some time because the data is very large. Then after I finish running all these code chunks, then I will have the realized volatility for the stock one, and for stock one and corresponding to its first 500 time IDs. So let me wait around 1 minute. It spends more time than I thought. So after these codes, oh yeah, now it finishes. After I run this code, I can compute the realized volatility for all the 30-second time bucket for each time IDs. Then remember, we have 500 time IDs, and each time ID is a 10-minute bucket. And for each 10-minute bucket, we have 20 realized volatilities because we divided each 10-minute time interval into 30-second non-overlapping intervals. Now I can just say I look at one specific time ID, that is time ID 5. Then I can look at the time series for the log returns and the time series for the volatilities. And you can see the time series for log returns is very noisy, but you can see that the mean of the log returns is near 0, meaning that in a short term, say in just 10 minutes, if we do not use any advanced predicting or statistical models, we cannot make any money from this 10-minute bucket, right? The price or the log returns of this stock is just I think, goes up and down across zero. So the mean for the log returns within such a short interval, 10-minute interval, is just zero. And for the realized volatility, still remember we have 10-minute time bucket, and we divided this 10-minute time bucket by 30 seconds. So the resulting time point is 20. So you can see that there are 20 number of time points here, meaning that we have 20 30-second intervals, and for each interval I can compute a corresponding realized volatility. Okay, this is just the preliminary analysis and some visualizations of the time series of the log returns and the time series of the realized volatility. And then based on this data, I can do some analysis. So before doing the analysis, I can compute the autocorrelation of this time series. So I can just run this code. You can see that this is the ACF, autocorrelation function, for the time series of the log returns. And this is the ACF, the autocorrelation function of the time series of the realized volatility. So to understand the autocorrelation function is something like this. So we have a time series. So if there is no lag of this time series, then I can consider a copy of this time series. So if these two time series has no lags, then I can see these two time series are identical. Then the correlation between these two identical time series must be 1, right? Because we just look at two identical vectors. So here, this is why when the lag is 0, the autocorrelation function is always 1. Then I just have 1 lag. So this is the original time series. I have 1 lag, something like this. So I consider the correlation of this time series for the overlapping part. Then I can see the autocorrelation is something like this. So it is something like a strong negative autocorrelation. And then I can just increase the lag. Now, lag 0, lag 1, lag 2, something like this. And you can see now lag 2, the autocorrelation is near 0. So meaning that there is nearly no autocorrelation for the time series after 2 lags. This is for log returns. And for realized volatility, you can see that the correlation of this data can be quite high, but you can also see that this is the something like confidence intervals. So when these vertical lines exceeds these confidence intervals, you can see that there is a strong autocorrelation of this time series. But since we only have 20 realized volatilities for the for this time series, so you can see that the confidence band is quite wide. So usually this autocorrelation function does not tell us much information about the ACF of the time series of the realized volatility. But you can see from the autocorrelation function of the original time series for the log returns, the confidence interval is quite narrow, so that you can see that it indicates a very strong negative autocorrelation here, because you can see the magnitude exceeds this confidence interval is very large. So it's just some preliminary analysis of these two time series. Then I have 3 benchmarks to analyze these time series. The first benchmark is regression. So regression does not treat the original data as a time series data. So but it does some regression analysis, say that the price at the realized volatility at time t is some function of the covariance at time t minus 1. Say I predict the realized volatility at time t is a linear function of the mean prices at time t minus 1, the mean number of orders at time t minus 1, and the mean beta spread at time t-1, then I have a linear regression model. I believe these three covariates will affect the realized volatility in the next period. Then I just compute the corresponding coefficients of these linear regression models. So let's look at how we do it in R. So first, remember, this is a time series analysis. We need to split the data set into two parts, the training part, the training data set, and the validation data set. We only use the training data set to train the model, linear regression model or HAV model, Armagosh model. Later on, we will also use this training data set, and the remaining 20% of the data set is used as testing data set or validation data set. So I just say for a time series, I extract the first 80% of the data set as training data set, and the remaining 20% is the of the validation data set. So this code essentially say for each time ID. Remember, I installed all the data in a list. So each element of this list corresponds to a specific data under a specific time ID. So for each element of this list, I just extract the first 80% of the data as a training data. Remember, we have 10-minute bucket, 600 second, and we divided this 600 second into non-overlapping 30-second intervals. So we will have 600 divided by 30 equals to 20 intervals. Okay, so the first 80% of the data is just the first 16 data points of the corresponding data frame, right? And then this is the training data, and I just remove these data points to get the validation data set. So now I use this for loop to split the data into training data, 80% of the data, and validation data, 20% of the data. And now the first method is the regression analysis. Remember, if you still remember the linear regression, it's just y equals to x times beta, right? Y is your response vector, x is your data matrix, your design matrix, and beta is the coefficients I want to estimate. So essentially, the code here is to formulate the design matrix in R. So remember, we have three predictors. The first predictor is the mean price in the previous period. The second is the mean number of orders in the previous period, and the third is the mean beta spread for the previous period. And our response is the realized volatility in the current period. Okay, so why we need to use the covariates in the previous period to predict the current period? Because it's a prediction problem, right? Say now I am at time t. The only information I can get is the covariate information at time t-1. So I cannot use the information at time t for prediction. I can only use the information at the previous period for prediction. That is why we look at the mean price, mean number of orders, and mean beta spread in the previous period. So now here I just had this code here is just add a new column to see what is the number of orders in every second of the last period, and this is just the index. So if it is in the first 30 seconds is 1, second 30 index is 2, the third 30-second interval is just 3, something like this, and it uses the same strategy as before, so that later on we can use the aggregate function to see what is the mean number of orders, mean weighted average prices, and the mean beta spread for each 30-second time intervals. And now with these two columns added, now I can use a for loop to compute the corresponding design matrix. Now what covariates do I need to compute? 3 covariates, right? The mean weighted average prices in the previous period, the mean number of orders in the previous period, and the mean bid-ask spread in the previous period. So I just using the aggregate function here. The same strategy as before to compute the realized volatility. I use the aggregate function here, and the corresponding function is mean. So I just compute the mean of the weighted average price in each time epoch, the mean number of orders in each epoch, and the mean of the bid-ask spread in each epoch. Now I can compute these three covariates for all the data points, for all the 30-second time intervals. And I also have the realized volatility for all the 30-second intervals. So I just have one leg. Remember, I need to use the information at time t-1 to compute the realized volatility at time t. So I just lag here. So this is why you can see here the I information for the volatility, the index for the volatility and the index for these covariates have a one lag. So essentially, we're just using the information in time t-1 to predict the information at time t. So at the first glance, this code may be very frightening, but you just say you can let I equals to 1 and all the variables you have, just run this code line by line, and then you will see, oh, it works like this. So this is, from my perspective, the most efficient way to see how this code works. Just if you have a for loop, just say I just let I equals 1 or 2, any number within this range, and run the code line by line within the for loop, and you will see, oh, this is why this code works. Okay, then essentially, as a summary, this code essentially is computing the design matrix of a linear regression model. Remember, y equals to x times beta. X is the design matrix, and y is the response vector. It essentially just compute the y and x for this linear regression model. Based on this design matrix, I can use R to compute the coefficients of this linear regression model. And I think everyone here should be very familiar with this linear models function, right? We just tell R, I want to use linear models, and the response is the realized volatility. I will use mean price, mean number of orders, and mean I spread in the previous period to regress the volatility on these three covariates so that we can make prediction in the future. This is just the ordinary least squares. But remember, this is the time series data. So if we just use the ordinary least squares, we overlook all the time information. So a more robust way in practice is to use the weighted least squares if we want to use a regression model. So the weight is determined by recency. So here I use a exponential weight 0.8 to the power of the recency. So how to understand this code here? So now remember we have 600 seconds for one 10-minute time interval, and we divided this 10-minute time bucket into 30 seconds non-overlapping time intervals. So 600 divided by 30 is 20. Now we only look at the first 18% of the data as training data set. So the last point here is 20 times 0.8 is the 16th point. It is the last point in our data set, right? Then I just say, if now I am at time 16, this is the most recent one. So the weight should be 1. And if it is time 15, then we have one leg, right? The most recent one is 16. If it is 15, then it is 0.8, from 1 to 0.8. Now, if I am at second 14, then it's 2 legs, 16, 15, 14, 2 legs. Now the weight becomes 0. To the power of 2, 0 square, 0.64, something like this. So the weight is just exponentially decreases. So this code here is essentially compute such exponentially decaying weights. Okay, so then I just tell this is a weight, and then the LM function, instead of running an ordinary least square, it runs a weighted least square, and we can just find one model for each time point. So this is what I want to emphasize here. Remember, for the whole data set, we have 127 stocks, and for each stock, we have multiple 10-minute time intervals. So for all the benchmarks in this lab, we construct a model for each pair of the stock ID and time ID. So we just treat each 1 10-minute time interval to be independent. We overlook all the correlation here. So meaning that in this step, we look at stock 1, we have 500 time IDs. Then we will have 500 different linear regression models and independent to each other. And this is what you can improve. Say we have so many stocks, so many different 10-minute time buckets. You can propose a huge model that jointly analyze the data across different stock IDs and across different time IDs. So this is what I believe there is much space to improve compared to this very naive benchmark models. So after I run in this for loop, I will have I should run it here. After I run this model, I should have 500 linear models, and it takes some time to run. And again, here, this bucket, this chunk essentially computes the design matrix and the response vector for the linear regression. And after we got the data, this chunk here essentially computes the linear regression models for each time bucket, for each 10-minute time bucket. So remember, we look at 500 different time IDs. So this means that we will have 500 different linear regression models for this benchmark. Okay, and you can see that I just pick one of the 10-minute time bucket here, and you can see that the R square is 0.74. It is very satisfactory because it is a real world data, right? So we just use some 3 very simple covariates to make prediction, and you can see that the price is the most significant one. The number of orders and the beta spread is not significant, right? The p-value is very large. So for the price, it is significant, meaning that in practice we can use the mean price in the previous period to predict the realized volatility in the next period. But actually, this stock ID is the best one. So this time ID is the best one. For other time IDs, for other 10-minute intervals, I think the result is you can see the R square is just 0.1 to 0.2, meaning that it does not have a very good fit of the data. So this is for the linear regression model. And the second benchmark is the HAVRV model. So it means the heterogeneous autoregression, vector autoregression realized volatility model. So the HAVRV model is very popular in long-term prediction of the realized volatility. But in this lab, we only have 10-minute data set. So this model may not perform very well for such a short-term prediction, but we still include this model here as a benchmark, such that you can compare your own models with this HRV model in your final in your final report. And for the HAV-RV model, it essentially predicts the realized volatility at time t based on the realized volatility at time t minus 1, the previous realized volatility, and the mean realized volatility in the previous 5 periods, and the mean realized volatility in the previous 22 periods. So if you think of t equals to 1 day, then the previous 5 periods is just like the mean realized volatility in the last week, and the mean realized volatility in the previous 22 periods is just something like the mean realized volatility in the past month. So it has a nice physical interpretation, but for short-term prediction, like we just have a 10-minute data and we want to predict the realized volatility in the next 30-second intervals, and this model can perform not very good. And because we only have 10-minute data, we divide it by 30-second resolution, then the resulting time point, what is the number? 600 divided by 30 is just 20 time points. So if we just have 20 time points, we cannot say we compute the mean realized volatility in the last 22 periods, right? The time series is too short to compute this thing. So for this benchmark in this lab, we only use the realized volatility in the past periods and the mean realized volatility in the past 5 periods to predict the volatility, the realized volatility in the current period. Okay, so now essentially this for loop is just to compute the mean realized volatility in the last 5 periods. Say, essentially, this code is very difficult to understand, and you can try to run this code by yourself to see how it works. So essentially, we just look at, now this is the first time point to say some points. I define it here is to be j plus this line's minus 6, and later on I will explain what it is. So just this kind of time series. And then this is j equals to 1. J equals to 2, I just move this time window to one step further. This is j equals 2. J equals to 3, I just move this time window one step. J equals to 4, I move this window. J equals 5, I again move this model. Now I have 5 time series. If I just take the column mean of this time interval of this 5 time series, I can get the mean realized volatility for the first 5 periods, for the second 5 periods, for the third 5 periods. This is essentially what we did for this for loop. So remember, if you add the sixth time point as second 6, then what is the previous five period? It is 1, 2, 3, 4, 5, right? So essentially, the first element of this vector is just the mean realized volatility in the first 5 periods. So this is can be very confusing when you first look at this code. So my suggestion is that you run this code by yourself and you print this result and see what does it represent. It essentially just represents the mean realized volatility in each 5 consecutive 30-second time intervals. And then I can use this vector as one of the features in the HAV-RV model, because HAV-RV model needs the mean realized volatility in the past 5 periods. And this for loop essentially computes this value. And in addition to the mean, to the mean of the previous 5 periods, the mean realized volatility in the previous 5 time intervals, we also need the realized volatility in the previous time interval, right? So actually, this is just this line here. This is the realized volatility in the previous periods, and this is just the volatility in the current periods. So essentially, this is our y, and this is our x. So although HAV-RV model is a time series model working on the time series of the realized volatility, but it's still a regression model in essence, because it just regress the current realized volatility on the previous realized volatility and the mean realized volatility in the past 5 periods. So essentially, it does this thing. Okay, then with this data matrix, I can now use linear regression to fit the model. So remember, HAV is a time series model, but essentially it does linear regression. So the most simple ways to do regression is to just use ordinary least square. So here I just say this is our y, our response is the realized volatility. I just regress this realized volatility on the volatility in the last period and the mean realized volatility in the previous 5 periods. And I just run here. And this is the most simple one, the ordinary least square. And this ordinary least square performs the best if the arrow term, say, if you still remember Andy's excellent lecture, the HAV model, there is the arrow term called UT. So if in practice the variance of UT does not change over time, does not change over t, then ordinary least square is the best model. But especially in finance, usually the arrow term of the time series is time dependent, meaning that the variance of this noise term UT is not constant. So if this is the case, a more robust method or more efficient method is to use the weighted least squares. And the weights here we use is just the realized volatility in the last period divided by the square root of the realized quantity in the last period. And this formula is also available in the lecture notes. So we just essentially, the code here just essentially compute the corresponding quantity. And then I just input this formula, the realized volatility divided by the realized quantity. Here, say the weight is realized volatility divided by the realized quantity. The weight is here, just the copy paste of this mathematical formula into R. Then this is a more robust, more efficient method using the weighted least squares to fit the HAV model. And you can also see that if I cherry pick a time ID, so the 218th time ID of stock 1, you can see also, oh, wow, this HAV model performs quite well. You can see the R square is 0.8, but for most time IDs, the R square is very low. It's less than 0.2, I think. So it means that there is a lot of space for you to improve the prediction performance for the HAV-RV model. And then the final benchmark is the Armagarch model. So remember what are the first 2 benchmarks? The first benchmark is a linear regression. So for linear regression, it does not treat the whole data as a time series data, but it introduces some weights, and the weight is based on the recency of the data point. So this is the first strategy. The second strategy, the second benchmark is the HAV-RV model. So the HAV-RV model directly predicts the time series of the realized volatility. And the third benchmark here is the Armour-Gauge model. So Armour-Gauge model, instead of modeling the time series for the realized volatility, it models the time series of the log returns. So remember, realized volatility is computed from the log returns. So if we just can simulate the dynamics of the future log returns, we can just sum these log returns, sum the square of these log returns up and take the square root. Then this is just your predicted realized volatility, right? So realized volatility is computed from the log returns. Now, rather than we directly predict the future realized volatility, now I predict the future log returns. Based on the simulated log returns, I can indirectly predict the realized volatility. Okay, so let's look at how this works in R. So remember, we have loaded a package called UGARCH, and to use this packages, I first need to tell R what is our model. And remember, in our lecture notes, we use the most basic one is Armour-Gauge model. So the Armour part is for the conditional mean. If you still remember in this lecture, the Armour part is for the conditional mean, and the Gauge part is for the conditional variance. So I just say the main model here is just a basic Armour model, and the variance model here is S here should mean simple. It's the simple Gauge model. And then I need to determine three things: the order of the Armour model, the order of the Gauge model, and the distribution of the noise. So here, I just say the order of the Gauge model is 1, 1. Remember, we have two orders for Gauge model, two orders for Armour model. And here I also say Armour model, the order is 1, 1. And you can try different orders to see different prediction results and see if the orders will affect the final prediction result for the realized volatility significantly. So this is just the order for Armour and Gauge. And then I can say what is the distribution of the noise. So here I use maybe the commonest one. I assume the data has a normally distributed white noises. And you can also think if your noise is very large, so you can also specify a T distribution for the distribution model here. Now, after I specify the Armour-Gauge model, then I can just directly plug this specification spec variable here to UGARCH fit function. So it essentially uses this function to fit the data. So this is the specification of this model. I have determined the order for Armour-Gauge and the distribution for the noise. And this is our data. So the original log return data. It is not the time series of the realized volatility. It is the time series of the log returns. Remember, we look at the first 80% of the data for training data and use the remaining 20% for validation or testing. So I just look at the time smaller than 480 seconds. So what does it mean? So we look at 10-minute data. 10-minute data has 600 seconds. So 600 times 80% is just 480 here. So essentially, it just pull all the training data set of this time series for on the log returns and then feed this data. And the solver here, we use a hybrid. There are many kinds of solvers, but some of them are more efficient, some of them are more robust. So a hybrid solver is a more robust solver. If you use some other solvers, it can be quicker to estimate the corresponding model parameters, but it could raise some error if your data looks very strange. So because we have too many data sets, I just use hybrid solver here to yield a robust estimation of this the Armour-Gauge model. Okay, this is a more robust way. And similarly, as the previous cases, remember we have 500 time IDs. For each time ID, I feed a separate model. So meaning that we have, if we use linear regression, we have 500 linear regression model. If I use HAV-RV, I have 500 HAV-RV model. And here I use Armagach. Essentially, I just have 500 Armagach model for the whole data set. Then, after fitting the data, how can we indirectly predict the realized volatility? So the strategy is I have captured the dynamics of the time series of the log returns. So to predict the realized volatility in the next 30 time intervals, I just simulate the log returns in the next 30-second period, and then square them, sum them up, and take the square root to obtain the corresponding realized volatility. This is our strategy. And we can simulate a large number of such time series such that we can then average them together, take the mean to get a more accurate result of the estimate of the realized volatility. So here is the code. So after I have fitted an Armagach model, I can use this getSpec function to extract the original order of the ARMA model, original order of the Gach model, and the distribution of the white noise process. So after I get this fspec function, I can just put this fspec function to a simulated function. This simulated function called ugauge path. So essentially, ugauge path predicts the future time series for a given period. Say we want to predict the realized volatility in the next 30 seconds. Then I just say I want to simulate the log returns in the next 30 seconds. So this is why n.sim equals to 30 here. And to because we use simulation-based method, simulation always contains some noises. So to make this method more robust, more accurate, I just repeat this simulation for 1,000 times. So I just simulate 1,000 different time series of the log returns in the next 30 seconds. For each time series, it is corresponding to a realized volatility, right? And then I can just take the average of all these 1,000 realized volatility to get a prediction of the realized volatility in the next 30 periods. So here you can see that after I fit the path here, I have a time series for the log returns. So for all the log returns, I just square them, sum them up, and then take the square root. So after this, we will have 1,000 different estimates of the realized volatility in the next 30 periods. And then I just take the average of the 1,000 realized volatilities to get 1 point estimation of the realized volatilities in the next period. And one small thing I need to mention here is that if I use this ugauge path model to simulate the future time series of the log returns, sometimes there can be some numerical issues and it will generate an NA value. So essentially this line is just replacing all the NA values with 0. And in your own project, you can try different strategies to deal with the NA value here. I just use the simplest one, just replace all the NA values with 0. Now this is just all the 3 benchmark models: regression model, HAV-RV model, and Armagach model. These 3 models use different strategies to analyze the original time series data or snapshots of the order book data. Then we need to use some performance measures to assess how good the model is in predicting the future realized volatility. So for simplicity, in this lab, we only assess the performance of the linear regression models in the validation data set. So remember, I use the first 80% of the data set for training and the remaining 20% for validation. Now, if I want to use a linear regression model to do prediction, remember, linear regression model is something like y equals to x times beta. Y is response, x is design matrix, beta is coefficient. And now I have beta, right? Because I have fitted the data. I need to construct the new design matrix, new x, so that I can predict the corresponding y. So the code here is actually constructing the design matrix based on the validation data. It looks nearly the same as the one when we train the linear regression model. When we train the linear regression model, we use the training data to construct the design matrix X and use LM function to fit the data. Now I have the validation data. I use nearly the same code. You can compare this code to the previous one when we fit the regression model. It is nearly the same. Now just essentially using the validation data set to construct this data matrix. Then with the linear regression model, with the design matrix, I can use a function called predict to forecast the corresponding y. What is y? It is the realized volatility in the next period, right? Then this is our prediction for each time IDs. Remember, we have 500 time IDs, and for each time ID, we will have 4 predictions. Why? Because we have 20 realized volatility. We divided by 600 into different non-overlapping 30-second intervals. So the number of 30-second intervals is 20. So we use 80% of this data point. So meaning that we use 16 out of these 20 data points, and the remaining 4 are used for validation. So for each of the 4 data points, we will have a prediction. And remember, we have 500 time IDs. So the total number of predictions we have will be 500 times 4 equals to 2000. Okay. Yeah, this is the prediction part. And with the prediction, we can assess the performance of this prediction using some performance measures. And in this lab, we will mainly use 2 performance measures. The first is the mean squared errors, and a very common performance measure used in time series analysis and nearly all prediction problems, right? And the second one is more popular in such realized volatility application scenario. It is called quasi-likelihood. And Q-like is more robust performance measure, and it performs better than MSE if there is some outliers in the original time series. So the formula for MSE and Q-like are both available in the lecture notes. So for MSE, it's just the true value minus the prediction, and I square them. I take a mean. So I think everyone here should be very familiar with this performance measure. It's essentially compute the MSE. And for the quasi-likelihood, we also provide a formula. It's the true value divided by the prediction minus the logarithm of the true value divided by the prediction minus 1. Then you just follow the original formula and type them in R. And then you remember we have 2000 predictions. I can just make box plot for MSE and makes the box plot for quasi-likelihood. And this is just for the linear regression models. And in your own project, you can try to use HAV model and Armagosh model for prediction and compare the performance of different methods in terms of the MSE and the quasi-likelihood. And one last thing I want to mention is that this prediction is just a static one-shot prediction scheme. So we have the validation data, we have the training data. I just use this training data to feed the model, and just for one time. And now I don't change model anymore. And now I just compare, do one-step prediction, two-step prediction, something like this. But another prediction scheme is called a rolling window prediction. So for time series, every time if I see a new data, I fix a time window and I feed a new model and use this new model to make the prediction. And in your own project, you're also encouraged to say what is the difference. It is rolling, horizon, scheme better, or just one-shot estimation method is better. So the one-shot estimation saves time, saves the computational effort, but it may not be that accurate compared with the rolling horizon models. And you can have a comparison in your own project. And this is all for week 4A lab. And thank you very much.